my name is Ben Palmer, and this is my project for week 8. This week I decided to do still keep it simple because MATLAB just doesn't seem to be my forte, but I feel like I got a better grasp of it this week in keeping it pretty simple. But I wanted to make a thumbtack, and to do that, I basically just wanted to flatten the nail head in the example, which is body 1. I just wanted to flatten that out and widen it, and increase the radius to widen it out to look more like a thumbtack. So here's the code for that. Really, the biggest change is to flatten it out and widen it. I did in the parameterization is 6 times r cosine theta or t, and then 6 times r sine t. The only thing that you had to make sure of here was that you accounted for this in the Jacobian down here, so there's that 6 again. And then also down here, you can see where these 6's are put in throughout the code to make sure that they align with the parameterization. The output for it, for the force acting on the body, was 1583, and this is surface 1. So the normal vector is just pointing up. It's acting on that surface. So 1583 in the x1 direction, 1583 in the x2, and then 3166 in the x3. And then just like I was showing you earlier, here are the stress fields as shown. And then this is basically the shaft of the thumbtack, and then this is the head of the thumbtack, just flattened out and expanded. So here I defined the Cauchy stress tensor field, which was symmetric. And this is the same as what was used in the example, but I just had to account for it later on in the calculations. To parameterize a thumbtack, like I said earlier, it was just the 6r cosine theta and the x1, x2, 6r sine theta, and then x3 stayed the same. It just had to be accounted for, just like in the code here, but you can just see a little better where this would be 12r cosine theta instead of 2r cosine theta. And then 6r cosine theta and 6r sine theta, because this is x1 plus x2. This is x1 plus x3, x1 plus x2, and so on, just like up here. And then here is the surface that I wanted to define. So I wanted to get the traction field, or compute the traction field acting on that surface. And that's shown here. So it's 6r cosine theta plus z, and then 6r sine theta plus z, and then 2z in the x3 direction. And then we wanted to find the total force acting on the surface, which this is this equation here, the double integral of x1, x2, x3 times r d theta dr. And that ends up being 126 pi 2 squared, which is equal to 1583 in the x1, 1583 in the x2, and 3166 in the x3. And like I was just showing earlier, here's the output from MATLAB, and that ended up being exactly the same. So that concludes my presentation for week 8. Thank you so much.